welcome back to Fat Mama Physics. Here is the second video on Hooke's law, so more examples. I'm going to do example 3, you're going to do example 4, and there is a challenge accepted, a bonus question I hear down below, which I will go over together with you. So without further ado, let's get started with example 3. We have a 2.5 kilogram mass placed on a spring scale that depresses it by 5 centimeters with the mass on top. What is the spring constant of the spring scale? Okay, so here I am going to just write down, actually draw a picture of what we have here. Here we have a mass on the spring scale. Mass is this blob that I have here, which is not specified in the question. Here I have a spring, and here I have the base for the reading. So here the mass, because it has weight, it will depress the spring scale, and as a restorative force, think of it as retaliation, the spring will want to push back at this mass here with an equal and opposite force, the spring force. And since this mass is not moving, these two forces are equal and opposite. So we know acceleration here is 0, and the fact that the force of the spring force, will be equal to the force due to gravity because there is no acceleration. Okay, so then we know that Fg is equal to mg, and that the spring force is equal to kx. And again, I didn't put the negative sign in there because I have determined the direction of that force already in my Fnat equation when I drew the free body diagram. So the negative sign is not needed. So I'm going to substitute all of these inside my equation here. I get, and to solve for the spring force, the spring constant, I divide both sides by my displacement to get mg over x, in which m is given to me 2.5 kilograms, gravity as 9.81, and the displacement is as 5 centimeters, which we will need to convert to meters by dividing by 100, moving this decimal place twice, 1, 2, giving us 0.05 meters. So putting that all in, okay, and substituting that, putting in the calculator, I get 4,905, which I'm going to round to 2 sig figs, so 4,900, and the units for spring constant is Newton per meter. Cool, okay, so that was fast. Yours is probably going to be the same. So let's just make sure you get you understand what you're looking for. A purse loaded with coins is hung from a spring scale with a spring constant of 54 Newton per meter. The new equilibrium position is 2 centimeters below the spring's natural equilibrium position. Find the mass of the purse with coins. So that's what you don't know. And you might be wondering what this natural equilibrium position, what is this new equilibrium position, what does it mean? I here have a quick simulation just to show you what that is. Okay, so here I have a simulation also with Fnat. There is 2 springs here. I have set them to be the same spring constant for our convenience. And the question is us putting a purse or a mass on a spring scale, which will then stretch the spring out. So this simulation is very similar to that. So let's just put a mass here and see what happens. Yes, that's the first thing that will happen. But what we can do to, what we need to do now is just to hold the mass in place so it's not doing this oscillation thing. More on oscillations later in the course. So let's pause that, okay? Or not so pausing it. What that's doing is we're taking the mass and just stabilizing it so it doesn't oscillate. Notice what happens when we do that is this mass will displace the spring down from the original equilibrium position. What's that going to establish is a new equilibrium position, and I can show us that by clicking this here, mass equilibrium. So that's the new equilibrium position that this mass creates by stretching the spring. So now it's the forces are balanced. The spring force is balanced with this force due to gravity here. That's our new equilibrium position once we have a mass there. Sure, of course, I can kind of oscillate it, and notice that if I just get the mass going, it will oscillate relative to that new equilibrium position. Okay, but either way, that's not the important thing. The important thing is you're trying to find out how much this mass will displace that original equilibrium position to this new one. And that's when the two forces are balanced. Okay, so hopefully that gives you a little bit of idea to help you solve for example 4. Otherwise, this is a good time to pause. Alright, and I will put my solutions on fast play.
First of all, let's draw a free body diagram, and we have the purse that is stretching the spring there away from its old equilibrium position, and since it's not moving, the force due to gravity is balanced by the spring force, and which the spring force is kx, and Fg, and force due to gravity is just mg. We substitute that in, solve for mass, and we get the following. Putting in our numbers in our equation, don't forget to convert the 2 centimeters into meters by dividing by 100, and after we calculate that out, we get 0.11 kilograms.
Okay, so here's our solutions. As the purse was being hung on the spring and placed at the new equilibrium position, the force due to gravity balances with the spring force, which then we have a very similar situation to the previous problem, except this time we are solving for mass and not for the spring constant. And then we get 0.11 kilograms, which is 110 grams. Okay, so now we are done with that. We have a challenge accepted, so we're going to take on this challenge here. And I will go over this one together with you. If the spring scale carrying the purse in example 4 was accelerated upwards at 0.98 meters per second squared, calculate the new equilibrium position. Ooh, that's okay, so let's figure this out. What does it mean? Okay, so a spring scale kind of looks like this if you haven't seen one in class or in a lab yet. So it has a hook on the end, which we can hang mass from, similar to this simulation that we have here. The spring is embedded inside this little box, so you can't see it. So let's draw a picture. So here I have a really bad picture of a hand, a finger through the hook over here, and this person with the spring scale, imagine, will pull on the spring scale upwards. By pulling the spring scale upwards, something is going to happen to the spring. What do you think? Do you think the spring is going to stay the way it is? It will stretch, or will it compress? I want you to think about that. And if you say that the spring will stretch as a result of this hand pulling the whole thing upwards, you are correct. So why does a spring stretch? That's because it feels the inertia of the purse, and for a split second, it's going to stretch, and of course, if your hand continues to apply that same force, it will continue to be stretched out as thus. If you have a stretched out spring scale, what does that mean in terms of the spring force? Is it larger or is it less than before? And if you say it's going to be larger, and since the spring is being stretched out, it's going to apply an equal and opposite force back towards its original equilibrium position. So expect a larger spring force relative to the force due to gravity acting on the purse itself. And that just shows the fact that we have an upwards acceleration for the purse, and in order for that to happen, and it does make sense because the spring's force has to be larger than the force due to gravity. So that's my free body diagram. Spring force is upwards, force due to gravity is downwards, and Fs is going to be larger than Fg. Now I can write my Fnat equation now. I have the upwards direction being the positive direction, so I'm going to, for my Fnet, if it's going to be the spring force minus the force due to gravity. We know that the spring force is kx. Don't need the negative sign because I know the directions already. Fg is just mg. I'm going to substitute these in here. I get kx minus mg equals to ma. That's an x. And now I am going to solve for x, which is what I want to find. I want to find the new equilibrium position. So I want to find how much my spring will need to stretch in order for my purse to have this upwards acceleration. First, I need to move the mg to the other side. Then I can divide both sides by k to get x by itself. We know the mass. We know the mass from the previous problem. We know the acceleration due to gravity. The question says the acceleration we want is 0.98 meters per second squared, and the k, the spring constant, is given in the previous question, which I believe is 54 Newton per meter. Substituting all that in and putting that in our calculator, making sure that we use the mass value without rounding, we get 0.02199. So that rounds up to be about 0.022. We can check if that makes sense. What that translates to is, moving backwards, that gives us about 2.2 centimeters, which is just 2 millimeters higher than the original displacement of the purse when it's not accelerating. So having accelerate does stretch it by 0.28 centimeters. So yes, it does make sense. Here's our challenge accepted. Hopefully you learned a little bit from this video and that will help you with your practices. Thank you for watching this video, and Fnat Mama Physics signing out.